Okay, so the momentum principle you're going to hear a lot about this semester. It's probably the single most important idea that you're going to encounter in Physics 107. And when we write the momentum principle symbolically, it looks pretty simple. It's just an equation that has three terms in it. What it says is there's this quantity that we call the change in momentum, and that's determined by the product of a force F times a time duration or interval delta t. So to really understand, there's a lot embedded in this equation. To really understand what's going on, I'd like to start with a simple example and show you how to apply this momentum principle to that simple example. So the example that I've chosen, okay, so you've all probably seen something like this. This is called Newton's pendulum, this little toy. A lot of people have it on their desk because it's fascinating to watch. You've got this row of hanging steel balls, and you pull one back and you let it go, and they sort of click back and forth. So that's a little bit too difficult to analyze as a first example of the momentum principle. So let's take a somewhat simpler case. Let's just take the case of two balls, one of which is just hanging stationary vertically down, and the other ball, the one on the left, we pull back and we let go, and let's see what happens. So what you notice is that the ball that was initially stationary acquires some momentum, some velocity, and hence some momentum, and the ball which was initially moving comes essentially to rest. So what I'd like to do in this very first example is to analyze the first collision that we observed in this simple two-ball case. That is the collision in which the ball on the right is initially stationary and the ball on the left comes in with some momentum, and the ball on the left comes to rest, acquires zero momentum, and the ball on the right acquires some right-going momentum. Okay, so let me illustrate the situation this way. Let's call the ball that was initially stationary, we'll call that ball A, and the ball that was initially moving we'll call ball B, and I'll indicate that ball B is the one that's moving by putting a little arrow, right-going arrow on it. And this is what I'm going to call our initial situation. Then the balls collide, and after the collision, what we notice is that ball B has come to rest, and ball A has acquired some momentum. So we're going to call this the final. So initial is before the collision, and final is after the collision. Okay, now I'd like to make this somewhat quantitative. So I'm going to give numerical values to the momenta that appear in this problem. And I'm going to base the numbers I'm going to write down, I'm going to claim are sort of in the ballpark or what are reasonable for the actual situation that we saw in the video clip. So what I'd like to do is I'm going to call the momentum that ball B has in the initial condition, I'm going to call that P sub B sub I. And it has a momentum. Momentum is a vector, remember, so we have to specify three components. But the momentum in this case is all in the x direction. B is moving horizontally to the right. There's no y or z component to the momentum. So the x component has a value of 0.02 units of momentum, and the y and the z components of ball B's momentum in the initial case is 0, and the units here, remember, for momentum are kilograms meters per second. And ball A initially, of course, is stationary, so that's easy. It has all three components of its momentum are 0. After the collision, it's ball B that is stationary. So in the final state, so we're going to call ball B's momentum in the final state P sub B sub F, and all three of ball B's components are 0 in the final state. And it's ball A that now has in the final state a non-zero right-going momentum. And I'm going to assume that the magnitude of this momentum is also 0.02 kilogram meters per second. And that sort of looks reasonable if you look at the video, that the momentum that ball A acquires in the collision has the same magnitude as the momentum that ball B had before the collision. Okay, so to apply the momentum principle, the first thing that you want to get in the habit of doing is this equation, delta P is equal to F times delta T. You have to decide what is the system that you're applying the equation to, and what constitutes the surroundings of that system. So we're going to get in the habit of identifying a system by drawing a dotted line around it. And I'm going to choose to analyze the collision. I'm going to choose as the system ball B. So I'm going to put a little dotted line around ball B. And everything inside that dotted circle constitutes our system, and everything outside that dotted circle constitutes the surroundings. Another thing I want to get in the habit of doing is, when I write the momentum principle, really emphasizing the fact that on the right side, the force that's involved is the net force that acts on the system. So there could be a number of different forces acting on the system. Net force, remember, means that we have to add all those individual forces together to get the net force. Okay, so I've chosen ball B as my system, and what that means is, if I want to analyze the change in momentum that occurs during the collision, I am calculating the change in the momentum of ball B. So by definition, a change in momentum is a final momentum minus an initial momentum. So the delta P, the change in momentum for this system, is obtained by calculating the final momentum of ball B and subtracting from that the initial momentum of ball B. So in this case, the final momentum of ball B, remember, is all 0. And what that means is that when we calculate this vector, remember, the way you calculate a difference of two vectors is to subtract component by component. So to calculate the first component here, I want to take the x component of PB sub f, which is 0, and subtract from that the x component of PB sub I. So when I do that, it's 0 minus 0.02. So the x component of the change in momentum is negative 0.02. And then the y and the z components are both going to be 0, of course, because we're just subtracting 0 from 0, and we get 0. So the change in momentum of ball B that occurs during this collision can be written this way: minus 0.02, comma 0, comma 0 kilogram meters per second. So if we look at our equation for the momentum principle, what we are able to say is we've calculated the change in momentum of our system. The momentum principle says something about what causes that change in momentum. You could think of the right-hand side, F net times delta T, as sort of the cause, and the change in momentum of the object is the effect. So I would say that there's a net force acting on the object, acting for over some duration of time, delta T, and that is what's responsible for causing the momentum of ball B to change. Now, in this case, there's not too much more we can say because we don't have any information about direct information about delta t or F net independently. We don't have a way of knowing how long this force acts. Most of the net force is due to the force exerted by ball A on ball B. There are also forces of gravity acting on ball B, and the force of the string that's holding up ball B is also acting. But by far, during the collision, which lasts for a very short amount of time, by far the dominant contribution to the net force is the force that ball A exerts on ball B. So what we can say, one definitive thing that we can say is that because the change in momentum is left going, it points in the negative x direction, it must be true that the net force that acts on ball B also points in the left direction. Okay, so the last thing I'll consider in this example is we chose ball B to be our system, and that's how we've analyzed the momentum principle so far. Suppose instead we chose ball A to be our system. So I'll draw this in red. And I'd like to calculate the change in momentum of ball A. Well, the change in momentum of ball A is just the final momentum of ball A minus the initial momentum of ball A. And the final momentum of ball A is 0.02, 0, kilogram meters per second. And the initial momentum of ball A is 0, 0, 0. And that's equal to, when you subtract, you get a final momentum of plus 0.02, 0, 0. And in the interest of space, I've left off the units, but the units are, of course, kilograms meters per second throughout. And I know it's hard to read because I didn't write neatly, but it's plus 0.02 is the x component of the change in momentum of ball A. So how do the changes in momenta of ball A and ball B compare? Well, notice that the change in momentum of ball A has the same magnitude but the opposite direction to the change in the momentum of ball B. And what that must mean is that the net force that acts on ball A is of equal magnitude but opposite direction to the net force that acts on ball B, because the duration of the forces is presumably the same. The balls are in contact for the same period of time, so delta t is the same in both cases. The net force that acts on A, therefore, is equal in magnitude but opposite in direction to the net force that acts on A. And boy, was that boring.